gases behave as they do?
After all them changes that you put me through, you stole my money and my cigarettes, and I ain't seen how to have you yet. I wanna know, oh, will you tell me, just tell me how could I stay here with you? Oh, will you take me to the river and wash me down? Just take me to the river and put my feet back on.
Well, welcome back, class. Why do gases behave as they do? Well, in this video lecture, we're going to talk about the kinetic theory of gases. And remember, theory means grand explanation. So our explanation for the way gases behave. And the tenets of the kinetic theory of gases are as follows. The size of a gas molecule, or a gas atom, is extremely small compared to the volume occupied. The average kinetic energy, Ke, the little bar on top means average or mean. The average kinetic energy is directly proportional to temperature. And the third important tenet of the kinetic theory of gases is that collisions between gas molecules, or gas atoms, and the walls of the containers, or between the collisions between the gas molecules or atoms themselves, are essentially elastic. That is, they don't stick once they collide. Now, a couple of things to consider. 1 mole of water vapor, gaseous water, occupies 22.4 liters at STP conditions. STP 273 Kelvin, 1 atmosphere pressure. Remember? Because it's like most gases, it occupies about 22.4 liters. However, if these water molecules were condensed to the liquid phase, liquid water, what volume would they occupy? Think about it. It would occupy 18 milliliters, or 0.018 liters. Now, what in your experience is a volume of about 18 milliliters? Well, I'll give you one example. About half of a shot glass is 18 milliliters. And if it were the solid state of water, it would be an ice cube, is about 18 grams or 18 milliliters in volume. Now, to a first approximation then, when the gaseous water, condenses, it occupies about 0.1% of the available space. So if we consider that in a condensed phase, the water molecules are close to one another or touching each other, that means that in a gaseous stage, they are much expanded and they're not touching each other. And in fact, the water molecules in the gas phase actually occupy only about 0.1% of the total available space. Before going on to the next slide to illustrate this, I wanted to also show you this equation, that the average kinetic energy is proportional to temperature. That's the second tenet of this kinetic theory of gases. Also, you may recall the equation that you've seen probably a number of times. Kinetic energy is 1/2 mv squared. We'll get to this again in another slide or so. But let me give you some visual cues about the space occupied by a mole of gas, mole of gaseous water, or a mole of liquid water, or a mole of solid water. And that is shown in this slide, where you see 3 basketballs. Remember, 3 basketballs occupies about 22.4 liters. So if water vapor were filling these 3 basketballs, that would be the approximate volume occupied. If the water molecules, 1 mole of them, were condensed to the liquid phase, it would be about half of a shot glass, about 18 milliliters. And if water were in a solid phase, it would be like an ice cube, 18-gram ice cube. The point is that in the gas phase, water molecules occupy approximately 1,000 times the volume that they occupy in the liquid or solid phase. Or in other words, when you form a gas phase, the molecules or the atoms greatly expand to a volume that is approximately 1,000 times the volume of the corresponding condensed phase, liquid or solid. Now let's go back to this relationship involving the average kinetic energy, Ke bar. Now we said before, average kinetic energy is 1/2 mv squared. In this version of the equation, for some reason, scientists, when studying the motion of gas molecules, like to use U for the velocity instead of V, and let's just say, okay, that's the way you'll see it in many textbooks. So the U essentially is velocity. And notice that I have a bar on top, or a hat on top, of both the average kinetic energy and the average velocity, U bar. And we'll see why we have to talk about averages a little later, because there's actually a distribution of velocities. Now, for M, the M in this equation is the mass of an individual molecule or atom, but then we've also added in this equation Avogadro's number, N. So N is Avogadro's number, M is the mass per atom or per molecule, and of course the product of Avogadro's number times the mass per atom or molecule is equal to the molecular weight, just so that you'll understand the factors in this equation. So average kinetic energy is 1/2 Avogadro's number times the mass per atom or molecule times the average velocity squared. Now it turns out, and this is a little bit more advanced theory, that the average kinetic energy is also equal to 3/2, 1.5, 3/2 times R times temperature. The reason to present this to you is that you'll see we'll need it for the couple equations below. Now let's take the average or mean velocity squared of the molecules and take the square root of it. Okay, that sounds like you're going forward and backwards one step, but let's take the square root of the average squared. This is something called the root mean square, URMS, the root mean squared velocity. The mean is the average, we squared it, and then we took the square root of it, the root mean squared velocity. Now from this root mean squared velocity and combining that with the equation above, you can actually derive the next equation that says that the root mean squared velocity of a gas molecule is equal to the square root of 3RT divided by the molecular weight of the gas. Now this gives you a handy relationship between the root mean squared velocity, which can be considered the linear velocity of a gas molecule. If a gas molecule was just moving linearly, it gives a relationship between that root mean squared velocity and temperature and molecular weight of the gas molecule. You can see that the root mean squared velocity is directly proportional to the square root of temperature and inversely related to 1 over the square root of the molecular weight. Now what this equation says is that smaller gas molecules will diffuse faster and larger gas molecules will diffuse more slowly. For example, the root mean squared velocity of a hydrogen gas molecule at standard conditions is about 2,000 meters per second. I mean, that's hard for us to even imagine, 2,000 meters per second. Well, so let's take another one. The root mean squared velocity for nitrogen gas is about 500 meters per second. 500 meters is about the length of 5 football fields. So what this means is if you started the nitrogen gas molecule at one goal line, and in 1 second it would be able to travel linearly 5 football fields. That's how fast a gas molecule can translate, or that's its linear velocity. So we can do this calculation of root mean squared velocity for any gas if we know the molecular weight of the gas. Now, one thing to note, if you look at some of the problems in the textbook, that the R value that you use for these problems is a different R value. It has a different constant. So make sure that you take note of that so you don't get frustrated in trying to work the problem. Also, another concept besides linear velocity, root mean squared velocity, how fast the gas molecule is moving, another concept that is somewhat related is what is called mean free path. That is, how far will a gas molecule translate linearly before it strikes another gas molecule? Well, clearly that depends on pressure, like how many gas molecules are in the container, but let's say under STP conditions of 1 atmosphere, it turns out that a gas molecule will translate or will move linearly a pretty long distance before it randomly just strikes into another gas molecule. That's because everything is really spaced out in a gas. Now, to give you some perspective, let's imagine that a gas molecule is as big as a football lineman, and that the diameter of a gas molecule or football lineman gas molecule is about a yard. Now, most of our linemen are not that big, but they're close to a yard in diameter. If our football lineman gas molecule were linearly translating, moving in a straight line at its particular velocity, the mean free path of a gas molecule that big would be like 3 football fields before it would strike another lineman gas molecule. The point is from this example that in the gas phase, the atoms of the molecules are really spaced out. So they rarely strike each other. And that is one of the properties of being a gas. That is, the atoms, the molecules are spaced out. They don't interact with each other. and there's just a lot of void. Now these two graphs illustrate some of the concepts of the equation that we had in the previous slide. The top graph shows the relationship between a molecular speed, that's root mean squared velocity, and the molecular weight of the gas molecules. But also it shows that the gas molecules are not all moving with the same linear velocity. There's actually a distribution of these speeds or these velocities. The shape of this distribution is something called a Maxwell-Boltzmann distribution. And if you look at the top graph, you see that the gas molecule that moves the fastest is hydrogen. Now, of course, it's a broad distribution. The hydrogen molecules, being the smaller, have a larger molecular speed, or root mean squared velocity. As we had in a previous slide, their average might be something like 2,000 meters per second. Then we go down to helium, hydrogen gas, nitrogen, oxygen. Nitrogen peaks out at around 500 meters per second, as we said in the previous slide. The point is that the smaller things move more rapidly and the larger things move more slowly. And again, using our football analogy, the cornerbacks and the halfbacks, the smaller players, move more rapidly and the big linemen move more slowly. But in each of these cases, it's a distribution. There are some molecules that move very, very slowly, and there's always some that move very, very rapidly, and we have to look at the sort of distribution and the average. The second bottom slide shows the effective temperature on the root mean squared velocity of gases. And here we're looking only at nitrogen gas, but the different profiles, the different distributions are for different temperatures, from 100 degrees Kelvin up to 1,000 degrees Kelvin. And this shows that as you increase temperature, things move more rapidly, which is what you expected. If you lower the temperature, the distribution shifts to the left, to the lower velocities. If you increase temperature, the distribution shifts to the right, you increase the velocity. Another interesting, somewhat useful phenomenon that we'll talk about is the effusion of gases. Have you effused today? Well, maybe, maybe not. But what do we mean by effusion of gases? Well, surely you've bought a balloon for a birthday party for yourself or for a friend or for your niece or nephew or something like this, and you go to the store and you buy this balloon, and it's filled with some gas, and you bring it to the party and everybody's happy. And then the next day you might see that this balloon is all shriveled up. It's like a sad little balloon. What has happened? Well, the gas molecules have leaked out. Now, gas molecules are very small and they can leak out of many containers. Unless the walls of the container are pretty thick, gas molecules can often diffuse through or effuse through the walls of the container. And if you're buying a balloon, some balloons are made of material that are less penetrable to gases, and others are more penetrable, so the gas will leak out faster from some balloons than others. Now, we can treat this effusion of gases using the kind of equation that we had in the previous slide, where we had the root mean squared velocity is equal to the square root of 3RT divided by the molecular weight. And this would say that if we compared two gases, one which has a larger molecular weight and one which has a smaller molecular weight, which one would effuse more rapidly from the balloon? That's right, the one with a lower molecular weight, or the smaller gas molecule, would effuse more rapidly out of the balloon. And this equation shows you the ratio of the rate of effusion, RA, or RB, for two different gases, A and B. The rate of effusion of two different gases from a balloon. And it shows that this ratio of these rates, rate of effusion or leaking out, is equal to the square root of the inverse ratio of the molecular weights. So a typical problem is that you might know the identity of one gas and not another, and you measure the rates of effusion or the ratio of these rates, and you can determine the molecular weight of the unknown gas. So these are some concepts related to the kinetic theory of gases. Now, in the next video lecture, we're going to go into cases where we have a breakdown of the kinetic theory of gases, and we will talk about what we call non-ideal behavior of gases. So we'll see you shortly.